Welcome to the deep dive. We take the fascinating sources you send us, and we dive deep to pull out the key insights. And today, we're tackling something huge. Humanity's dream, maybe even our plan to actually live on Mars. Our mission here is to unpack all this, cut through some of the hype maybe, and look at the real possibilities, the enormous challenges and the amazing tech that might just get us there. You sent over some really great research, so we're ready to get into it. Prepare for some surprising facts that'll get you up to speed fast. So the big question hangs there, doesn't it? Is calling Mars home just, science fiction, or is it getting closer? Let's dive in.
It really is shifting, I think, moving from pure sci-fi towards, well, a massive engineer puzzle, a really, really tough one. But before we start picturing neighborhoods on Mars, we have to face the harsh reality. The Martian environment itself, it's fundamentally, brutally hostile to life as we know it.
Brutally hostile.
Yeah, that sounds about right. Stepping out there wouldn't be like a rough day on Earth. It's something else entirely. So let's really dig into how different, how dangerous it actually is.
Exactly. Okay, first off, the atmosphere. It's incredibly thin, like less than 1% of Earth's pressure. And it's about 95% carbon dioxide. So forget breathing. Without a pressure suit, the low pressure means your actual blood would boil. It's, yeah, unbreathable.
Okay, boiling blood, not a great start. What about just, staying warm?
Right, the temperature. The average, mind you, is around minus 65 degrees Celsius. That's minus 85 Fahrenheit. And at night, it plummets down to maybe minus 125 Celsius. Just unbelievably cold. Any habitat needs serious thermal control just to function.
Wow, okay. Thin air, extreme cold. But you mentioned something else, an invisible threat, radiation. That sounds like a really big deal for staying there long term. It absolutely is. It's a game changer. See, Earth has this wonderful magnetic field and thick atmosphere that shield us. Mars doesn't. It lost its global magnetic field billions of years ago, and the thin air offers almost no protection. So anyone on the surface is exposed to radiation levels. Maybe it's up to 50 times higher than here on Earth.
50 times. So what does that actually do to people?
We're talking serious health risks. DNA damage, which leads to a much higher risk of cancer over time. It's not just an inconvenience, it's this constant silent danger that dictates everything about habitat design, mission length, everything.
And it doesn't stop there, right? The sources mention issues with water and even the soil itself.
Correct. There's no liquid water just sitting on the surface. We know there's water ice, mostly at the poles and buried underground, but getting it and using it isn't simple. And the soil, the regolith, it's full of toxic perchlorates. Not exactly great for farming.
Oh, toxic soil. Lovely. And didn't the sources also mention dust storms, like
Yep.
planet-wide ones?
Oh, yes. These aren't your average terrestrial dust storms. Martian dust storms can grow to cover the entire planet and last for months. They block sunlight, which is a huge problem for solar panels, potentially coat everything in fine dust. It's a major operational hazard. Imagine your power source just dwindling for weeks on end.
Okay, so summing it up. Thin, unbreathable air, freezing cold, lethal radiation, toxic dirt, and planet-choking dust storms. It sounds daunting. So what does this all mean for actually keeping people safe, let alone comfortable? How do we even start to shield ourselves?
Well, this is where the ingenuity comes in. We have to think differently. For radiation, one of the smartest ideas is actually using Mars itself as a shield. Building habitats underground is a key strategy, maybe using natural lava tubes that we know exist there, or simply burying modules under several meters of Martian soil, the regolith.
Ah, so the regolith, the Martian dirt, actually becomes useful as shielding.
Exactly. It provides significant natural protection from that radiation. So the very thing that's a bit troublesome on the surface becomes a key resource when you go underground.
That's clever. Turning a problem into part of the solution. Are we talking small shelters, or could you build whole communities down there?
The long-term vision is definitely for communities.
Yeah.
And besides using natural features or just burying habitats, there's research into advanced materials too. Things like special radiation-resistant polymers, or even processing the regolith itself, maybe mixing it with binders, to 3D print structures right on the surface that still offer protection.
And what about the trip there? That 6 to 9 month journey is still a long time to be exposed.
Absolutely. Spacecraft shielding is critical. We're looking at robust layers, maybe using water tanks sandwiched in the hull, or materials rich in hydrogen. These absorb or deflect a lot of the harmful particles. Honestly, without solving these shielding problems, both for the journey and on the surface, long stays just aren't going to happen.
Okay, so shielding is priority number one. Got it. But then, how do you actually live there? Build things, get water, breathe, eat, when you're millions of miles from Earth? The logistics seem staggering.
They are. And that's why something called ISRU, in situ resource utilization, is not just helpful, it's absolutely essential. We just cannot afford to ship everything we need from Earth. The cost is, well, astronomical. Some estimates put it around $500,000 per kilogram with current tech, maybe more.
$500,000 per kilo?
Yeah.
Okay, yeah. So you have to live off the land, so to speak.
Pretty much. You have to use what's already on Mars. So that water ice we talked about, we need ways to get it.
Right. How do you mine ice when it's, incredibly cold and possibly deep underground?
Good question. Technologies being developed include things like microwave heating systems to sublimate the ice, turn it straight into vapor, or maybe laser drilling. Then you capture that vapor and condense it back into liquid water. It's complex, definitely needs energy, but it's seen as feasible. And that water isn't just for drinking, it's for hygiene, growing plants, and you can even split it into hydrogen and oxygen for rocket fuel.
And speaking of oxygen, we can't ship tanks for everyone forever.
No way. But here's some amazing news. NASA's MOXIE experiment. It's an instrument on the Perseverance rover. It has already successfully made oxygen from the Martian atmosphere.
Really? It actually worked on Mars.
Yep. It pulls in the thin Martian air, which is mostly CO aero, and electrochemically splits the carbon dioxide molecules to produce pure oxygen. It's only produced small amounts so far, sort of toaster-sized production, but it proves the principle works on Mars. That's huge for future life support, and maybe even making propellant to come home.
That is incredible. Okay, so water, oxygen. What about building stuff? Habitats, labs, workshops? Can't ship those either.
Right. So again, ISRU. The leading idea is 3D printing. Using the Martian regolith, maybe mixing it with polymers brought from Earth or some kind of binder we can make there to print structures, think foundations, walls, radiation shielding layers, maybe even roads eventually. There's also potential for mining metals like iron from the soil. The goal is maximum self-sufficiency, using Mars to build Mars.
It's fascinating how every challenge seems to force this really clever, self-reliant thinking. Which brings us to food. The sources made it sound like turning Mars into a garden is, well, tricky.
Tricky is an understatement. Remember the toxic soil, the low sunlight, the cold. Traditional farming is pretty much out.
Yeah.
So the solutions point towards controlled environments. Hydroponics, growing plants in nutrient-rich water, and aeroponics, using a nutrient mist. No soil needed.
Like we do on the space station now.
Exactly like that, but scaled up. Experiments on the ISS have shown we can grow things like lettuce, radishes, other greens quite well using these methods. You'd have dedicated biodomes or indoor farms on Mars doing the same. Protected environments, artificial lighting tailored for plants, strict control over nutrients and water.
Is there any way to deal with the toxic soil directly? Like, could we clean it or make plants that don't mind it?
That's also being researched. Genetic engineering could potentially create crops that are resistant to perchlorates, or maybe even help break them down in the soil. But that's probably a longer-term solution. Hydroponics is more near-term.
And all of this, the air, the water, the waste, it has to be recycled, right? You can't just keep getting resupplies constantly.
Absolutely critical. That brings us to closed-loop life support systems. Think of it as extreme recycling. These systems have to recycle pretty much everything. Air gets scrubbed of euros, moisture from breath and sweat gets condensed back into drinking water, urine gets purified, even solid waste could potentially be processed. NASA's ECLSS system on the ISS is kind of the benchmark right now. It reclaims about 90–95% of the water on board. We need that level of efficiency, or even better, for a Mars base.
Wow. So OMOXI makes oxygen from the air, ECLSS recycles water and air inside. It's like building a tiny Earth in a box.
That's a pretty good way to put it. A very carefully managed, highly technological box, because failure isn't really an option when you're that far from home.
This all sounds incredibly complex, but sort of achievable piece by piece. But then you hear about terraforming, actually changing the whole planet. That sounds like pure science fiction still, doesn't it?
Yeah, full-scale terraforming, making Mars genuinely Earth-like with a thick atmosphere, oceans, the whole deal that is very much in the realm of science fiction for now. We're talking centuries, maybe millennia, if it's possible at all. The ideas thrown around involve things like releasing massive amounts of greenhouse gases, maybe importing ammonia from icy moons, or even, controversially, using nuclear explosions to melt the polar caps and release co-Euro and water vapor.
Nuclear explosions on Mars. Wow. But the sources mentioned some serious ethical questions around that kind of thing, too.
Definitely. A huge one is, what if Mars does have some form of microbial life, maybe hidden underground? Full-scale terraforming could potentially wipe it out before we even find it. That's a massive ethical consideration.
So maybe not planet-wide change anytime soon. What about smaller steps?
Exactly. The more practical approach, certainly in the coming decades or century, is localized terraforming, or perhaps paraterraforming. Think large, sealed biodomes. You can maintain an Earth-like atmosphere and pressure inside, grow plants in actual soil perhaps, maybe even have small bodies of water, basically creating Earth-like bubbles on Mars rather than changing the whole planet.
That makes more sense, like little practice runs for the real thing, maybe way down the line.
Sort of. And these biodomes would be invaluable as habitats and agricultural centers anyway.
Okay, so connecting this back from the far future to now, these aren't just abstract ideas. The sources highlighted some real tech breakthroughs happening right now that are pushing us closer.
Oh, absolutely. The progress in recent years has been pretty stunning, actually. The biggest headline grabber is probably SpaceX's Starship. This is designed to be a fully reusable launch system. The potential impact is enormous.
Reusable meaning cheaper, right?
Yeah. Much cheaper, theoretically, and bigger. It's designed to carry up to 100 tons of cargo, or maybe 100 people, per trip. If Starship becomes operational and reliable, it could fundamentally change the economics and scale of sending anything and anyone to Mars. SpaceX talks about crewed missions possibly in the early 2030s. That's ambitious, lots of hurdles still. But it shows the level of intent.
And NASA isn't just sitting back, right? They have their own plans.
Not at all. NASA's Artemis program is crucial. The focus is initially on the moon, establishing a sustainable presence there by the late 2020s, maybe 2028 is the target. But everything they're developing for the moon, new landers, surface habitats, advanced life support, the Gateway space station and lunar orbit, it's all technology and experience directly applicable to Mars. The moon is like a proving ground.
A stepping stone. Makes sense.
Exactly. Test it all out just 3 days away before you commit to a 6-month journey.
And it's not just SpaceX and NASA anymore, is it? Other players are involved?
Right. You have companies like Blue Origin developing their own heavy lift rockets and lunar landers. More competition, more innovation, more capacity. And critically, international collaboration is key. The European Space Agency, ESA, China's Space Agency, CNSA, they have active Mars programs, rovers, orbiters, plans for sample return missions. All that data is vital for planning human missions. It's becoming a truly global effort.
So we're seeing the rockets getting bigger and cheaper, the life support tech advancing, international partners contributing. It feels like the pieces are starting to come together. But stepping back, why? Why go through all this incredible effort and expense? What's the ultimate reason for humanity to reach for Mars?
That's the big question, isn't it?
Yeah.
There's several layers to the answer, I think. One major driver is, frankly, species survival. Having humanity established on 2 planets would be a powerful insurance policy against some catastrophe here on Earth, a giant asteroid impact, runaway climate change, you name it. Spreading out reduces the risks.
Putting all our eggs in one basket. Yeah, you hear that argument.
Exactly. But it's also about something more. Aspirational, perhaps. Pushing boundaries is kind of what humans do. Exploring, tackling immense challenges. It drives innovation. The technologies we need for Mars, ultra-efficient energy systems, closed-loop recycling, advanced robotics, telemedicine, these could have massive benefits back here on Earth, too.
That's a great point, the spin-off tech. But the source has also highlighted something else, the human side. It's not just about the engineering, it's about the people who go. That sounds like maybe the biggest challenge of all.
It could well be. We're talking about sending small groups of people to live in extreme isolation, in tiny confined spaces, millions of miles from home, for years. The psychological stress would be immense. No family nearby, no walking outside without a suit, no green landscapes, no easy way back.
Have we studied this? How people cope?
Yes. NASA and others run analog missions here on Earth, like the HIC's experiments in Hawaii. They put crews in simulated Mars habitats for months at a time to study the effects. And the findings are clear. Crew cohesion, psychological resilience, the ability to handle conflict and monotony. These are just as critical as technical skills, maybe more so. Selecting the right team, not just the right individuals, is paramount.
It really makes you think, if you were one of those first settlers, what's the one little thing from Earth you'd absolutely need to bring to stay sane? A picture, a certain food, music?
That's a deeply personal question, isn't it? And for future Martians, robust support systems will be non-negotiable. Things like virtual reality environments for recreation, maybe to simulate being back on Earth for a while, constant communication links, telehealth for mental health support. Coping mechanisms will be built into the mission architecture.
So the human spirit, our ability to adapt and endure, that's the final frontier within the final frontier.
You could say that. At the end of the day, the technology might get us there, but it's the people who will determine if we can actually stay and thrive.
Wow. Okay, what an incredible journey we've just taken just talking about it. Making Mars home. It's clearly one of the biggest challenges humanity could ever undertake. We've talked about the brutal environment, the need for shielding, for living off the land with ISRU, the advanced life support, the food production, the rockets, and maybe most importantly, the human psychological factor. It's daunting, no doubt. But with things like Starship, Artemis, and all this global innovation, it really does feel closer than it ever has before. So, could humans really call Mars home someday? As the sources suggest, the answer seems to hinge on our ability to overcome these huge hurdles and, well, to embrace the unknown. Now, we definitely want to know what you think. Get into the comments. Do you think we'll see people living on Mars in our lifetime? Let us know if you agree or disagree with our take on this. We read the comments. And hey, tell us where you're listening from. We're really trying to see how far these deep dives reach around the world. Drop your city or country in the comments. Also, if you want more deep dives like this one and just generally want to stay super well informed on fascinating topics, you should really check out Mind Expansion Daily. That's where we find so much of the amazing research we use for these discussions. Seriously, head over to Mind Expansion Daily, and while you're there, please hit like and subscribe. It genuinely helps us keep producing these deep dives for you.
It really comes down to that drive, doesn't it? That human impulse to explore, to see what's over the next hill, or in this case, the next planet. Mars is that ultimate test right now. It's where our ingenuity, our resilience, it's all going to be put on display, hopefully for generations to be inspired by.
Couldn't agree more. Thanks for joining us on the deep dive. We'll see you next time.